Starting with the percent composition, there are 3 easy steps you can do to figure out what the empirical formula is. We're going to show you that here, and then also show you some of the variations you might see on that. So the first step is really simple. You assume that you have 100 grams of whatever the compound is. So we're going to assume that we have a big pile of carbon and hydrogen here that's a compound, and it's a 100-gram pile. So if we have a 100-gram pile, and 82.6% of that pile is carbon, then 82.6 grams of that 100 is carbon. Likewise, 17.4 grams would be hydrogen. And that's it. Now, a lot of problems you'll run into, they'll start by giving you the grams, and so you can often skip over this step. If you're starting with percents, though, that's how you get from being in a percentage form to a gram form. Second step is you're then going to convert those grams to moles. So we're going to take the 82.6 grams of carbon, we're going to divide by the molar mass of carbon, 12.01. And we're going to do the same thing with hydrogen, we're going to divide by its molar mass, 1.01. So just taking those numbers right off the periodic table. So 82.6 divided by 12.01 comes out to be 6.88 moles of carbon. And for hydrogen, this comes out to be 17.23 moles. Okay, so at this point, we're done. This is our ratio of carbons to hydrogen in this compound. However, those numbers aren't very helpful to us because they're ugly. There are a whole bunch of things going on with them. So the last step is we want to take the numbers and we want to make those numbers purdy. So we want to take these numbers and make them into much more useful forms. So to do that, you're going to take the smaller answer and you're going to divide every answer by that. And what that's going to do is that's going to keep your ratio of carbon to hydrogen the same, but it's going to change the numbers from being in these decimal forms to being something that's hopefully a little more integer. So 6.88 divided by 6.88 is 1 for carbon, and 17.23 divided by 6.88 is going to be 2.5 for hydrogen. So now we know that for every 1 carbon we have 2.5 hydrogens, which of course we don't want halves. So we're going to double both numbers, so we're still in the same ratio. Our empirical formula would be C2H5. Okay, so finding the empirical formula, this is our empirical formula. Now, a word on this. So C2H5 is our empirical formula. We don't actually know if that's our actual formula or not. Okay, in fact, if you're familiar with organic chemistry, you're probably like, well, that's probably not it. Probably not looking at a free radical. So what we can do from there is we can then add one more step at the end of this where we can figure out what our actual formula is, which is called the molecular formula. And here's the idea. You don't know when you look at percentages whether it's this or some multiple of this. If this had been C4H10, it still would have been the same ratio of carbon to hydrogen. It would still produce the same results for percentages. If this had been C6H15, the same thing would have happened. So our formula can be any multiple of this. We don't know which. So the thing you can do at the end is if you're given a molar mass of the actual formula that goes along with this, you can compare it to the molar mass of your empirical formula. So let's say, so if we look at the empirical formula here, it's going to be about 24 plus 5, it's going to be about 29.07 grams per mole. Okay, well let's say a second experiment was done after we figured out the percentages, and that experiment found that the molar mass was actually 58 grams per mole. Well, now we can look and compare these two numbers and say, okay, well this one's about twice as big, so I must need about twice as much of this stuff in order to get my actual formula. So my actual formula would be C4H10. That would be my molecular formula. This would be my empirical. Let's take a look at a second problem to kind of go through that again. So here we have grams of nitrogen, grams of oxygen. So we can skip over our first step, assuming 100 grams. We can skip because we're already in that point. So we have 17.36 grams of nitrogen and 39.64 grams of oxygen. So we're going to go right to step 2. We're going to convert to moles. So we're going to divide by 14.01. molar mass of nitrogen. And that comes out to be 1.24. And then we're going to do the same thing with oxygen with its molar mass, 16. Again, taking those right off the periodic table, this comes out to be 2.48. So you might already see this, but our last step here, we're going to go ahead and we are going to divide both by the smaller of the two, 1.24, which is going to come out to nitrogen being 1 and oxygen being 2. So our empirical formula is going to be NO2. Now for our molecular formula, it tells us our molar mass up here. So we have 92 grams per mole. So we want to look at what's the molar mass of our empirical formula. Switch colors back to empirical colors here. So we have 14 plus 16 plus 16 is going to come out to be 46 grams per mole, give or take a decimal or two. And we're comparing that with 92. Well, 92 is twice as much. So our molecular formula needs to have twice as much stuff, but still have 2 oxygens for every 1 nitrogen. So the solution to that is to double everything and have N2O4, which still has a 2-to-1 ratio, but has a molar mass of 92 grams per mole.